Hello friends, welcome to the today's lecture. In this lecture we will discuss the concept of variational derivative and some application of variational derivative. So if you recall, we have already defined variation and differential of the functional. For example, if we have a functional defined by this a to b f of x y y dash d of x, then we have defined the variation in functional j as j of say y plus h minus j of y, and this we have defined as this L of y. Here h is your delta of y. So here we can say that this we can write it L of y delta y and plus beta times, or you can say b y and delta y and maximum of modulus of delta y. So this we have defined differential of this functional j y as L of y delta y as the differential or variation of this functional j. Delta j is defined like this, provided that this beta y delta y is tending to 0 as maximum of modulus of delta y tend to 0. And here we have defined delta j as this, and we may also define it like this, divided by divided alpha j of y plus alpha delta y at evaluated at alpha equal to 0. So here this is the definition which we have discussed, and with the help of this variation, or we can say function variation of this functional j, we have derived the Euler equation, which is a necessary condition for an extremal to satisfy this thing. So if y is the extremal of this function j, then that must satisfy the Euler's equation. Now with the help of this, we can also define the concept of variational derivative, which is known as functional derivative also. So we want to see how we can define variational derivative or functional derivative. So if you recall, we can discuss the maxima and minima, or you can say extrema of a function of several variable with the help of partial derivative. So the necessary condition for finding the extremum of a function of n variable is that the partial derivative is equal to 0. So here we want to define the similar kind of quantity as partial derivative for the functional. So that quantity we call this as functional derivative or variational derivative. So we for this, let us define the functional j of y given as a to b f of x y y dash dx, with the condition that y of a is equal to capital A and y of b is equal to capital B. So to find out say variational derivative, we recall that we have discussed that the functional can be understood as function of infinitely many variable, and for that we have utilized the concept of Euler's finite difference method. So here also we use the method of Euler's finite difference and convert this functional into a function of infinitely many variable and try to relate the variational derivative with the partial derivative of function of several variables. So for that we first truncate this problem, this functional, into a problem of n dimension problem of a function of n independent variable. For that, and then we try to pass the limit as n tending to infinity and try to see what relation we will get. So for that we divide the interval a to b into n plus 1 equal part. So we say that x naught is a, xn plus 1 is equal to b, and all between element are divided into n plus 1 equal parts. And we can say that we can replace the curve y equal to y of x by the polygonal line with vertices this. This we can see it like here. So here we have a curve, say y of x like this, and this is your x equal to a, and this is your x equal to b. So here what we try to do, we divide this into n plus 1 equal parts such that your x naught is a and x n plus 1 is equal to b, and we simply say that this curve is approximated by these lines. Okay. So it is like this. So here it is this and this. So we are considering that this curve is approximated by these polygonal lines. Okay. So and here the value of this y of x naught is equal to a, and we define y of xi as y of I. So here if you look at the functional j of y, which is given as a to b f of x y y dash d of x, this can be approximated by the summation I equal to 0 to n f of xi y of I and y of I plus 1 minus yi upon delta x and delta of x. So here we are denoting y of I plus 1 as y of xi plus 1, and we denote this quantity, we define this quantity as say we can define this quantity as say j y1 to yn. So the difference is that here this functional is approximated by this function of n independent variable y1 to yn. Here please recall here that your y of naught, y naught which is given as y of x naught, it is already given as a, and similarly y of x n plus 1, that is y of n plus 1, that is also known, that is b. So it is basically function of n independent variable, that is y1 to yn. So here so it means that what we have done is that we have approximated the functional jy by this sum which is depending on the variable y1 to yn, and it is given as this summation I equal to 0 to n f of xi yi plus 1 minus yi divided by delta x. So here y dash is approximated by this sum yi plus 1 minus yi upon delta x. So here this notation we are using, that yi is equal to y of xi and delta x represent the length of the interval, that is xi minus 1. So now since it is a function of n independent variable, now let us try to find out say derivative of this j which is given by this sum with respect to say one of the independent variable, let us say this is yk, and try to find out the partial derivative this del j y1 to yn with respect to yk. So del j upon del yk we are trying to find out. So basically it is what, let us consider here somewhere say this is corresponding to your say xk. So this is your xk, and here this represent your y of k, and this is your xk minus 1, and here we have xk plus 1. So here we have this thing. Is that okay? So what we try to find out here, we have these straight lines here. Okay, we try to find out del j by del yk. It means that if we do a small change in the values of yk, if we perturb yk little bit, and then what is the corresponding change in this function j will occur. So that we wanted to check. So to find out del j upon del yk, let us consider the function given in this particular form, and then you find out del j by del. So del j by del yk. So del j upon del yk. And if you remember here this this yk will appear in two terms. First when I is equal to k, so when I equal to k, then we have yk here, and corresponding to I equal to k minus 1, there yk will appear here. So when you find out say derivative with respect to yk, then we will get f of y, and this I am considering for I equal to k term. So that is f of y, x of I, y of I, and y of I plus 1 minus yi upon delta x, and then you consider this particular term. So minus f of y dash, this position is corresponding to y dash, and here we have xi, yi, and yi plus 1 minus yi upon delta x, and here we have delta x, and then we have this is I equal to k. So, this is k plus 1, this is k plus k here, and then we when you differentiate this minus yk upon delta x, then you will get minus 1 upon delta x. So, this delta x will be cancelled, and now consider the term corresponding to I equal to k minus 1, which gives plus, and for corresponding I equal to k minus 1, here we have f of y dash, and we have x of k minus 1, y of k minus 1, and y of this k minus y of k minus 1 divided by delta x, and then when you delta x divided by because of this term you will have one more 1 upon delta x coming into picture. So, we will cancel this, and we can say that derivative j upon derivative yk is given by f of y x of I y sorry, this is I equal to k. So, here we can get I as k. So, I can write it here f of xk yk plus 1 minus yk upon delta x plus we write it in a different form. We can write it here f of y dash and x of k minus 1, y of k minus 1, yk minus 1 upon delta x minus this term, that is f of y dash here, and this is xk yk and comma yk plus 1 minus y of k upon delta x here. So, when you write it like this, and then if you take delta x tending to 0, so if I take the limit as delta x tending to 0 means as your this length of the interval is tending to 0, it means that the number of partition is tending to infinity. So, here if we are doing this, then just look at the limit here, then this term is tending to 0 because we have a delta x here, and if you look at these two terms, these two terms will tend to the same limit, that is f of y dash x y and y dash. So, here these two terms will also cancel each other. So, it means that we try to find out say limit of this saying derivative j upon delta yk into delta x, and then if you calculate this, then this quantity is basically what? This quantity will be f of y x of k y of k and y of k plus 1 minus yk upon delta x plus 1 upon delta x will be here, and here we will write this thing f of y dash and x of k minus 1, y of k minus 1 comma y of k minus y of k minus 1 divided by delta x minus this quantity f of y dash here. Now, now we try to take the limit of both the side as delta x tending to 0. Then please recall here the term in denominator here delta derivative yk delta x, this basically represent what? Derivative yk represent this term, this derivation, and delta x represent this thing. So, it means that this derivative yk into delta x represent the area between this shaded line and this this shaded line and this dark line. So, it means that this represent a kind of area, you can call this as say delta say yk, you can write it like this, or delta some sigma k, you can write it here. So, it means that you can write it like this. So, it means that if you say that this delta x tending to 0 means the area between this this dotted line and this dark line is also tending to 0, and then we want to find out say the change in the functional j. So, as you take that delta x tending to 0, then this will tend to what limit? So, we say that if delta x tending to 0 this limit exists, we call this limit as delta j upon delta y. So, this is the limit of delta x tending to 0 derivative j upon derivative yk and delta x here. So, the whatever limit will be, that is denoted by delta j by delta y here. So, this we are doing it here. So, as we have seen that this 3 represent the partial derivative of j with respect to yk, which we have just calculated here, and here we divide this 3 by delta x, then we can calculate dy z by dy yk delta x equal to this quantity. This is just we have written here. Now, as you take the limit delta x tending to 0, then if this last term will tend to some limit, we call this limit as delta j by delta y, which which is given by f of y x of y y dash minus d by dx of f of y dash x y y dash. That is clear here, that here as delta x tending to 0, this will tend to what? This will tend to, let me so to find out delta j by delta y, we take the limit delta x tending to 0 and find out the expression. Now, if delta x tending to 0, then this xk will say tend to x and yk will be y. So, you can write it delta j upon delta y, which is given as this f of y x y y dash minus, now here this will be what? Here if you look at this term, it is what? It is x of k y of k, and let me write it here in a clear manner. This term is your f of y dash and x of k y of k comma y of k plus 1 minus y of k upon delta x. So, if you take the limit of this minus this as delta x tending to 0, then this will converge to minus of f of y dash d by dx of f of y dash x y y dash here. So, we can say that your variational derivative of functional j with respect to y is given by this quantity, which is known as f of y minus d by dx of f of y dash. Now, if you recall the Euler's equation, then it is nothing but the left hand side of the Euler's equation. In Euler's equation, the necessary condition for a curve to be an extremum of a functional is that f of y minus d by dx of f of y dash is equal to 0. So, here if we want to define the same Euler's equation in terms of variational derivative, then we can say that Euler's equation is nothing but that the delta j upon delta y is equal to 0 for every x belonging to this interval a to b. So, your Euler's equation, I can write it like this. Now, here we may discuss one more interpretation of this delta j by delta y. Here if we look at what is this basically, here we are finding say limit of this quantity. Now, what is the limit of this quantity? Here this represent that here we have perturbed only the value of y only in the neighborhood of say xk. So, here we try to find out say partial derivative of this function j from y1 to yn with respect to yk. It means that in the neighborhood of xk we perturb the value of yk, that is we perturb the value of yk and try to see what is the corresponding change in the functional. So, it means that here this delta y, here we have considered the change only in the neighborhood of xk and we denote it as like this. So, in general we can generalize into a new concept or new thing. We can say it like this, that if let jy be a functional which depends on the function y of x, and suppose hx be the increment in y of x which is different from 0 only in the neighborhood of a point x naught. So, here if you recall we have done in the neighborhood of x of k. Now, let us say that x naught be a point in which we find out say different increment in y of x which is denoted by h of x. So, we say that dividing the corresponding increment j of y plus h minus j of y of the function by the area delta eta. What is the delta eta? Delta eta is the area lying between the curve y equal to h of x and the x axis. In fact, you can also consider that this delta eta is the area between the curve y plus h and y. So, here if you look at this quantity is j of y plus h minus j of y divided by delta eta. So, here if you look at if you find out say limit of this as delta eta goes to 0 is the same thing which we have considered here. So, here we can interpret this quantity delta j by delta y as you can simply say that it is nothing but you have j of y plus delta y here minus you can consider this as j of y divided by the area which delta y covered, that is you can consider that as delta eta. So, here we can say that what is the limit of this. So, this I can define as limit delta eta is tending to 0. So, we can also define the variational derivative in the sense of function like this. So, here we say that if the area delta eta goes to 0 in such a way that both maximum of modulus of hx and the length of the interval in which hx is non-vanishing go to 0. So, here your delta eta is basically what? Delta eta is the area of this saddle line and this dark line. So, here we say that this delta x tending to 0 and delta y is also tending to 0. So, it means that we are saying that this is denoted as delta eta. So, we can say that delta eta tending to 0 means the height is tending to 0 as well as the width of the area where it is non-zero. This h of x is non-zero, that is also tending to 0. So, here we can say that then if the ratio 5 converges, ratio 5 means this thing. So, if the ratio j of y plus h minus j of y divided by delta eta converges to some limit as delta eta tending to 0, we call this limit as delta j by delta y in the neighborhood of x equal to x naught, and we denoted this as this, and we call this as variational derivative of the function j y at a point x naught. And as we know that there are certain rules which ordinary derivative satisfy, the similar kind of rules we can also prove for this variational derivative. Now, moving on say next thing we can find out say relation between the variation and the variational derivative. So, here we can say that from the definition of variational derivative, it is clear that if hx is different from 0 in a neighborhood of the point x naught, and if delta eta is the area between the curve y equal to h of x and the x axis, then j of y plus h minus j y is equal to delta j by delta y defined at x equal to x naught plus epsilon into delta eta. In fact, you look at here. So, this is what this is, we have defined as delta j upon delta y, and if you remove the limit, then we can write it here this as j of y plus delta y minus j of y equal to, you can say that it is delta j upon delta y. Now, since we are considering delta y only in the neighborhood of point x equal to x naught, so we can write it at x equal to x naught plus, here you can take any function say epsilon into delta eta. So, as epsilon tending to 0, this delta eta is tending to 0. So, here we can define this is nothing but differential or variation of the functional. So, here we can say that we can link variational derivative and variation of the function in this way. Is it okay? So, here we say that delta j is given as j of y plus h minus j of y is equal to delta j by delta y given at x equal to x naught plus epsilon into delta eta. So, where epsilon tending to 0 as both maximum of modulus of hx and the length of the interval in which hx is non-vanishing go to 0. It follows that in terms of the variational derivative, the differential or variation of the functional jy at a point x naught is given by this formula. So, here you can say that the limiting case as epsilon tending to 0, we can say delta j is equal to delta j by delta y given at x equal to x naught into delta eta. So, this is the relation between variation and variational derivative of a functional j. So, as an application of variational derivative, we are going to discuss the problem of this property which is known as invariance of Euler's equation. So, what is this property? If you recall we have a j of y which is given as a to b f of x y y dash d of x. So here we are using the rectangular coordinate system x y and here we are considering that y is a function of y of x here. So now if we want to consider the same problem in some other coordinate system, and then it means that if we write it in some other coordinate system, say for example here we are using xy plane, but now let us suppose that we are considering the new coordinate system uv plane, and we can rewrite this problem as j of y1, say j1 of v as something like a1 to b1, say f1 of u v and v dash and du. Then what is the relation between the Euler's equation given in this case and the Euler's equation given in this case? Whether can we do this kind of change of variable here also, because this thing we can do it in a multiple integral. When we solve some kind of multiple integral, when we are stuck in some kind of problem, then we always try to find out a new coordinate system in which your problem is simplified and you can easily solve. So here also we try to find out a similar kind of thing here. So here let us consider this, that if we use curvilinear coordinates u and v instead of rectangular planar coordinate x and y, where x and y and u and v are related by this, that x can be written as function of u and v and y is a given function of y of u and v. Now since u and v and x and y are simply representing the coordinate system, so here we are assuming that this Jacobian over x y with respect to u v is non-zero. It means that xu, this determinant xu xv yu yv is non-zero. Then we can say that the curve given by the equation y equal to y of x in the xy plane correspond to the curve given by the some equation v equal to v of u in the uv plane. So if we do this, then we can change the functional into a new function which is known as j1 of v. So here how we can do this change? We simply say that this here your y equal to y of x is given by so the corresponding curve is given by v of u. So here x is given as x of u and v and y is y of u and v. So here we simply replace this as the corresponding value of x when x equal to a, then we can say that this correspond to some value of u equal to say u1. Similarly when x equal to b, you can say that u is equal to some u2, or the corresponding values are there, and here we can write it f x of uv y of uv, and to find out dy by dx we will use this formula that dy is given as dou y by dou u du plus dou y by dou v dv. So this we can find out as y of u du plus y of v dv. Similarly we can find out d of x, that is xu du plus xv dv, and we can find out dy by dx as, you can write it here, yu du plus y v dv divided by x of u du plus x of v dv. And if we assume that v is a function of u, then we can write this as y of u plus y of v, and here we can write it v dash. V dash represent the derivative of v with respect to u. So here v dash represent dv by du, and here we have x of u plus x of v and v dash. So it means that here dx we can write it here as x of u plus x of v dash, is it okay, and d of u here. So dx can be written as this. So it means that in place of dy by dx we can write it this quantity, that is y of u plus y of v dash divided by x of u plus x of v dash, and in place of d of x we are writing this x of u plus x of v dash and d of u. So, this we call this as, so corresponding value you can call it u1 and u2. So, this you can say that u1 to u2, this we call as a sum function which is given in terms of u and v, and we call this as f1 u v dash and du, and call this functional as j1 which is given in terms of v. So, here your extremal curve is y and here your variable is v, is it okay. So, now we say that if y is the extremal curve of this, it means that y satisfy the condition f of y minus d by dx of f y dash is equal to 0, then we try to find out that whether v will also satisfy the similar kind of relation or not. It means that we want to find out the relation that f1 v minus d by d of u f of v dash is true or not, f1 v dash is equal to 0 or not. So, this we want to check here. So, our claim is that if this is true, then this will also be true. So, this we want to prove here. So, here we show that if y equal to y of x satisfy the Euler equation del f by del y minus d by dx of del f by del y dash is equal to 0, then the corresponding to the original function, this is corresponding to original functional j of y, then v of u satisfy the Euler's equation corresponding to the new functional, that is del f1 by del v minus d by du del f1 by del v dash is equal to 0 corresponding to the new functional j1 v. So, here to prove this, that if 6 is true then 7 is also true, we use the concept of variational derivative. So, let us say that let delta eta denote the area bounded by the curves y equal to y of x and y equal to y of x plus h of x. So, here delta eta is the area bounded by these two curves, and delta eta 1 denote the area bounded by the corresponding curves. So, corresponding to y equal to y of x we have v equal to v of u, and corresponding to this y equal to yx plus h of x we have new curve, that is v equal to v of u plus beta of u in the uv plane. So, if delta eta represent the area between these two curves, then delta eta 1 represent the area between v equal to v of u and v of u plus beta of u in the uv plane. And we already know that the area is related by this formula. So, here we can simply say that if we have area delta eta and in xy plane and delta eta 1 in the uv plane, then it is related by this, that Jacobian delta eta is equal to Jacobian of delta eta 1, where Jacobian is given by x y with respect to u and v, which is given by this formula xu xv yu yv, which is non-zero by hypothesis. So, this we have already assumed that this is non-zero. Now, if you look at the equation number 6 represent what? This represent what? This represent that delta y delta j with respect to delta y is equal to 0. So, here, and this is how we are denoting this, we are denoting as, so the Euler equation for this functional is given by f of y minus d by dx of f y dash equal to 0, which we have seen that this is nothing but the variational derivative of j with respect to y is equal to 0, and we also defined this delta j by delta y as j of y plus h minus j of y divided by say delta eta and limit delta eta tending to 0. So, delta j by delta y is defined like this. So, it means the Euler equation means that this quantity is equal to 0. So, here we want to see whether this quantity is 0 in the new case also or not. So, here if you look at limit, now delta eta tending to 0, now j of y plus h is given by j1 of your v plus beta v of u, v of u beta v plus u, minus j of y is given by j1 of v, divided by delta eta I am writing as Jacobian and delta eta 1, right, and we want to show that this is equal to this limit is equal to 0 as delta eta tending to 0. Now we already know that delta eta is given by Jacobian into delta eta 1. So if delta eta is tending to 0, then delta eta 1 is also tending to 0. So we can write this as that limit delta eta 1 tending to 0, this I am writing as j1 v plus beta v delta v minus j1 of v divided by delta eta 1, and that is equal to 0. So this simply shows that this is nothing but in variational derivative sense delta j1 with respect to delta v is equal to 0, and which is equal to this thing, which represent that the Euler's equation in new coordinate system v is also true. It means that f1v minus d by du f of 1 v dash is equal to 0. So this simply says that if we have a function given in say xy coordinate system, then and y is the extremal of this functional, it means that this Euler's equation is true, it means this is true. Then in a new coordinate system, that is uv plane, the corresponding functional, so it means that we have seen that in new functional is also satisfy the corresponding Euler's equation. It means that if this limit delta eta tending to 0, j of y plus h minus j of y divided by delta eta is equal to 0, then this limit delta eta 1 tending to 0, j1 v plus beta minus j1 v divided by delta eta 1 is equal to 0, which simply says that the curve v satisfy the Euler's equation in uv coordinate system. So it means that property of a curve to be an extremal of a given functional is a property which is independent of the choice of the coordinate system. So it means that whether we have a say coordinate system which is xy coordinate system or say uv coordinate system, but the Euler equation in this equation and Euler equation in this system is independent of the coordinate system. So it means that this simply says that Euler's equations are invariant under the change of coordinate system. So here we have discussed the invariance of Euler's equation with respect to coordinate system, and next lecture we will discuss the example based on this property of invariance of Euler's equation. So thank you for listening us, we will meet in next lecture. Thank you.